Hello, my name is Brenna Argel. I'm faculty at Northwestern University, and this next session is session 12. Our first talk is entitled Cross-Modal Learning Filters for RGB-Neuromorphic Wormhole Learning, and the speaker is Alessandro Zanardi.
Hello, everyone. Thank you very much. In this talk, we present an extension of Wormhole learning. So we adopted an RGB camera and an event-based one to show that you can expand the operating domain of an object detector in a completely automated fashion. We introduced cross-modal filters that cope with the different representation that naturally arise when you look at the same scene with two different sensors. But what's the idea behind wormhole learning? So we have an operating domain, which is here represented as a plane, and we associate the x dimension with a certain nuisance, in this case, the scaling of illumination. On the z-axis, instead, we have the sensor modalities. We start off with a detector that works only at daytime, and we would like to make it work also at night. In order to achieve this, we do a little trick. We first switch domain, and we go to a domain which is inherently almost invariant to illumination. In this case, the event-based domain. So we train an event-based detector with the event stream and the inference from the RGB detector. As a result, now we are in a domain which is approximately invariant to illumination, so the world looks almost the same also at night. As you can see here, now we can move to the right of the figure, and the detector is still able to accomplish the task at night. Of course, the invariance is not ideal, so you can see from the shimmering lights in the street that the world looks a bit different, but still the detector is able to perform. So now we do a step which is symmetric to the previous one, where the student becomes the teacher, and it's the event-based detector that retrains the RGB camera. We can now get rid of the auxiliary sensor, and we're left with an RGB detector that works at night, as you can see here. So if we look at the algorithm, in 2 times, we use the data from one sensor and the labels from the other one to retrain a new detector. It turns out that this is not always the best choice, because you have problems with observability, as you can see here from the car. To this end, we introduce what we call cross-modal filters that cope with this different sensor representation. You can see them here represented as funnels in the 2 transfer learning steps. So cross-modal filters are functions that, given a pair of data and a detection, should tell us whether or not we should use that training sample for the new detector. Note that this is not the same as a detector itself, because we want to reconstruct the decision boundary only conditioned on having had a detection in one of the 2 domains. This function seems a bit daunting, but it turns out that for RGB and event-based cameras, it's quite simple to compute. We look at the generative model of the sensor, and we check if events appear at edge location where we expect them to be, and vice versa. Therefore, the cross-modal filters become a simple if statement. As a result, we see that we are willing to compromise a little bit of performance during day in favor of a significant gain at night. And what was more striking to us is that this works even though the middle modality is not particularly apt to the task. So please come and check the interesting details at our poster. Thank you.
The second talk is entitled PoseRBPF, a Rao-Blackwellized particle filter for 6D object pose estimation, and the presenter is Dieter Fox.
Hi, this is work Xinke Deng did when he was an intern with the NVIDIA Robotics Research Lab in Seattle, but he couldn't come due to visa issues. The goal is 60 pose estimation, where we have an object model, and then we observe a scene, and we would like to recover in that scene the position of the object, which is the 3D translation and the 3D orientation. Knowing that information, of course, can be useful for many tasks, such as manipulation and any kind of semantic reasoning about the environment. It turns out that reasoning about the uncertainty in the orientation of the object is actually a crucial component here. Let me give you an example. If you have a depth camera and you observe that object, from that view, you cannot recover anything about the orientation of the object or whether you're looking at the object from the top or the bottom. Now, if you imagine you have a color camera and you have a textured model of the object, then suddenly you can use the texture information to uniquely recover, of course, the position of the object, even from that single view. But even if you use a color camera and the view onto the object is like this, then from that view you still cannot recover whether you're looking at the object from the top or the bottom or what the orientation of the object is. It turns out that prior work has typically more or less ignored that problem, and they typically come up just with a single pose estimate, or they don't explicitly deal with symmetric objects. So last year, Sonnemeyer and colleagues came up with a really cool approach for symmetric objects, where they train a variational autoencoder that takes as input an image centered around the object, and from that they generate a 128-dimensional code. And that code is highly sensitive to the viewpoint on the object, but insensitive to lighting conditions or occlusions of the object. Once you train that autoencoder on an object, you can generate a code book of many different views onto the object, in this case more than 90,000. And when you get a new image of the object here on the left, you just compute its code, and then you do cosine distance against all the entries in your code book, and that gives you a similarity measure, and from that you can then recover what the view on the object is. And they showed in their paper that that approach was the first one that can really explicitly deal with symmetric views onto objects, but they didn't deal with uncertainty over the translation of the object, and they only looked at individual images and also didn't do full distributions over the orientations. So in this work, we want to build on that idea and do full 60 pose tracking over objects, where we're using a Rao-Blackwellized particle filter. And the key trick is we factorize the posterior into the 3D translation, which we sample, and the 3D orientation, where the 3D orientation, we compute a full posterior distribution for each particle that is discretized the 3D orientation space by 5 degrees, resulting in a discretization of more than 190,000 bins. Now, if we have an image and we have a particle that has a translation, that gives us now a unique bounding box for that image. We can compute for this bounding box now the encoding based on the work that you've seen on the previous slide. And the particle code that we now get, we compare against a codebook with 191,000 entries, and that gives us now the likelihood over the orientation space of that image and that object in the scene. And we can do this for all the particles, and we can now incorporate that into just standard particle filtering techniques. And here you can see one example, for example, where we're tracking the coffee mug. On the left, you can see the bounding boxes of different particles, and on the right, you can see the orientation distribution for one of those. And you can see, for example, also that as the handle of the mug comes into view, that the uncertainty in the orientation automatically gets decreased. Of course, we implement it on a GPU. We can do this at 20 frames a second. We can also do global localization, where we just sample 5,000 particles in XYZ space, and after 1 or 2 frames, the distribution collapses to the particle and to the correct kind of post distribution, and now with 50 particles, we can again track the object in real time. Thank you very much.
The third talk in this session is entitled DIViS, Domain Invariant Visual Servoing for Collision-Free Goal Reaching. And the presenter is Faritesh Siddiqui.
Hello everyone, my name is Faritesh Siddiqui, and today I'm going to talk about domain invariant and semantic aware robot policies for the context of visual navigation. So robots are good at doing physical tasks. However, human interacts with the world heavily with semantic objects. So can robots also understand semantics, and would that help them become domain invariant? So to articulate that, let's watch a video. In this video, the robot is tasked to reach a teddy bear. To be successful in doing these tasks, the robot needs to understand walkable areas, avoid collision collisions and target the target object, or recognize the target object. So you might argue that the world contains many other different objects and a huge number of different other environments. So instead of learning a repertoire of motion for doing different tasks, we ask the question, can we learn a single policy for doing a diverse set of semantic tasks? So by that we mean to how to learn a single model that can have zero-shot generalization to unseen situations. And essentially we are aimed to propose a method to become the domain invariant by disentangling semantics from physics. So to learn physics, we use a domain randomized simulation environment, and to learn semantics, we use static real images annotated by human. And we use their interplane to learn the policy. So in this work, we are using different scenarios, and in each scenario, the robot is tasked to reach a visually indicated goal, which usually involves taking turn around different room furniture. We propose DIViS, which is a network architecture that integrates physics and semantics. The physical aspect of the task that we're looking at involves collision avoidance. To do the collision avoidance, we use our previous work, CAD2RL. CAD2RL can find collision-free directions to navigate to different free spaces. And it has a fully convolutional neural network architecture. To learn semantics, we use an object localization network, which is pre-trained with natural images, which are static but are annotated by human. And this network also has a fully convolutional architecture. By concatenating the semantics and physics features, we train a control network that navigates the robot toward the target goal. And our control network is recurrent, which has a recurrent LSTM unit and is trained entirely in simulation. So for training our controller network, we use deep reinforcement learning by doing multi-step dense Monte Carlo rollouts. And although this controller is entirely trained in simulation, it can generalize well to real-world situations and unseen environments. So we have tested our method in various domain randomized simulation environments, and being successful in doing these tasks involves moving around different room furnitures in very confined spaces. And we have compared quantitatively with other results, and DIViS has outperformed other methods with a significant margin. We have also tested our method in real-world environments, both qualitatively and quantitatively. And all these real-world scenarios are entirely unseen at the training time. For doing the real-world test, we perform and use two different real robot platforms, which have different height and have different RGB cameras. As you can see, our method can perform well in diverse set of scenarios, such as reaching a chair in confined spaces, or an oven in kitchen, or an umbrella in outdoor, and many, many other scenarios. And roughly we have gained about 82% in real-world scenarios. To conclude, we propose to disentangle semantics and physics to learn domain invariant policies. And we use very cheap simulation and real data. For more details, please come to my poster. Thank you.
The fourth paper is entitled A Behavioral Approach to Visual Navigation with Graph Localization Networks, and the presenter is Kevin Chen.
Hi, I'm Kevin, and today I'll be presenting our work on topological navigation using graph neural networks. Typically, robot navigation is solved using metric maps, which requires computing the precise geometry of the environment. However, humans are able to navigate extremely well and don't require such precision. In this work, we ask the question, is it possible for robots to navigate without metric information? Our problem setup is as follows. We have a robot in a cluttered indoor environment navigating from a place A to a place B. In order to navigate without metric information, we need an effective map representation. We encode the topology of the environment as a graph. In this graph, the nodes represent different locations or junctions, And the behaviors correspond to the edges correspond to behaviors for getting from one node to another. For example, to get from node A to node B, we'll first turn left, follow the corridor, and follow the corridor again. In addition to the topological map and the navigation plan, we also provide the agent with visual observations of the environment in the form of depth images, and we provide the initial robot location in the map. Next, the agent needs to be able to localize itself with respect to the map. To do this, we use a graph neural network, here GLN. The GLN takes as input the topological map, the visual observations, and the last predicted position in order to compute the current estimate of the robot's location. Lastly, once the agent has localized itself, the question that remains is, how do we control the robot to effectively follow the navigation plan? Using the localization estimate from the GLN and the navigation plan, we can look up which behavior to execute next. Then, we execute the chosen behavior using a neural network, one for each behavior. The neural network takes as input the depth images and produces velocity commands. In total, we consider 5 different behaviors, which capture the necessary movements for traversing the environment. Our results show that they work well even in previously unseen cluttered environments. We evaluate our approach using average plan completion and success rate for reaching a destination. Our approach outperforms the baselines and works even better when combined with the particle filter, denoted here as GraphNavPF. However, on one particular area, the difference between our approach and the baselines is not significant. We hypothesize that this is because the environment is drastically different from the trained environments. Lastly, we show a qualitative result of our full model. The robot has to navigate autonomously in a large indoor environment. It starts in the top right room and has to navigate to a room all the way in the center of the image. We also show a baseline in light gray, which fails to make a right turn at the correct time. Note that to traverse this environment, the agent must navigate through lots of clutter. Please see our poster for more details. Thank you.
The final talk in this session is entitled Oil, Observational Imitation Learning, and it will be presented by Guohao Li.
Hello, everyone. We are from Kals in Saudi Arabia. I'm happy to be here and introduce our oil to you. So what is oil? Oil is an imitation learning method that can learn from multiple weak controllers and become a stronger one. Oil is an antiquated method. It basically has 3 steps. We first observe the most critical teacher as our critic, and then we hear our method. We basically update our method based on the best demonstration, and then we roll out our policy to a new state. In our experiment, we use a modular architecture. Basically, our network consists of possession network and control network. We design 6 tracks for training and 4 tracks for testing. In our experiment, we compare our methods to the teachers he learns from and the human baseline, and we also did a comparison with state-of-the-art methods, for example, behavior cloning, Dagger, and DTPG. We also did an ablation study for the different trajectory lengths. The first application we look into is autonomous driving. As you can see in the table, oil can outperform the teacher it learns from significantly and also can outperform all the baseline methods. And the other interesting application is UAV racing. You can see similar result can be observed here. Here is the video result of oil. At the left top corner is our oil, and the other video is the teacher's it learns from. We can see oil can learn to combine the best of the other teachers. Here is the results of oil and some human baseline. You can see oil can drive as fast as Esper and more precisely. Here is the video results of oil and the other learned method. You can see behavioral cloning tends to learn aggressive policy, and DIViS tend to learn noise policy. And because it learns from random inspiration, and Dagger learn conservative policy. Here is the result of UAV racing. We can observe a similar phenomenon here. Behavioral cloning learn to fly very aggressive. The DIViS one learns to fly very noisy, and the Dagger one learns to fly very slowly. Yeah, our conclusion is oil can outperform all the teachers it learns from, and also the learned baseline. And oil is fairly robust to the hyperparameters, and learning from multiple teachers can generally improve the performance. Come and see our poster for more information.
Great. I'd like to invite all the speakers to join me on stage, please.
I have a question to the second speaker, Dieter Fox. I'm wondering how well does your approach perform when you have multiple instances of the same object type in an image, occluding each other?
Oh, yeah, good question. I think as well as the particle always works, which means accidentally what can happen that you have multiple clusters of particles in these individual objects, but otherwise, so we do not have an explicit multi-object version of that right now. So.
Any further questions? Yeah.
Yeah, thank you very much for the presentations. I have for you, for Lee. So does your imitation learning algorithms scale, not scale, but apply also to other kind of learning, or is only for driving? Does it can you use it to learn a robotic task, for instance?
Yeah, actually our method is a general framework. It can not only be applied to like drawing scenario, it can also be applied to like the other, like Atari game or something, I guess. Yeah.
Yeah, question for the fourth speaker. For the topological map, did you, how did you assign action costs for the different behaviors that you enumerated?
Sorry, did you say action cost?
Yes.
Could you elaborate on that?
Yeah, I think you have like different behaviors: turn left, turn right, go to door. And are there costs associated with those? Because in the topological graph, there's not necessarily the same representation as the grid world for Euclidean distance or some associated costs traveled.
Oh, Yeah, there's no cost associated with them. We just use actually behavior cloning to train the networks for executing the behaviors. And as long as they successfully take you to the next node, then that's all we care about.
So I have a question from Alessandro. I would like to know, do you think the same kind of transfer learning could be also applied, for dealing with different weather conditions?
What do you mean by better conditions?
Weather conditions,
Oh,
for
weather
example.
conditions.
Yeah. The rainy weathers or something.
Yes. The thing is that you need to find an auxiliary sensor that has some invariance characteristic with respect to your disturbance or your nuisance of the weather. So if you have a sensor, if you take, let's say fog, and probably with an infrared camera you can see through fog, then it could scale. Then of course you still need to have some signals in the region where you are trying to expand. Because if you have just pure fog and you can't see through also with the RGB, you will just learn the prior or where objects are more likely to be, but if there's no signal, you can't learn anything.
So I have a question for Dieter. It's very cool work. As far as I understand, you're using the Rao-Blackwellized particle filter to decouple the rotation for the translation part. Did you guys compare to sampling directly the 6 degrees of freedom and using just a particle filter on the pose?
Actually, no, we didn't do explicit experiments, but there's just virtually no way that you can keep track of these distributions, right? Because especially if you have, let's say, the circular uncertainty, your particles will very quickly collapse because you have this huge state space. Do you see? Because you have to sample X, Y, Z, and jointly you have to sample all these possible orientations. And when you do the resampling over time, you very quickly collapse to, let's say, one orientation or something like that.
Thank you.
Sorry for not being in line with diversity. I also have to ask Dieter something. So do you have a plan for actually do this in an unsupervised fashion, or do you have any ideas to actually scale this to situations where you actually don't have object models a priori?
Well, for the tracking in this sense, this is about tracking known objects, of course, right? I can imagine, and right now it has to be actually the autoencoder has to be trained for every object. We can do this fully in simulation, so that's kind of actually reasonably cheap. I can imagine that you could start training autoencoders that don't have to be trained on specific objects, but that just maybe on specific object classes or something like that. And then, of course, we're looking for manipulation. Of course, we're looking at techniques that don't depend on object models at all, but that's kind of orthogonal to this work here.
I have a question for the third speaker. You mention in your paper that you learn visual features in simulation that are robust enough to translate to the real world. I wondered if you saw any instances of features that were not robust enough to translate, and if you had any guidelines on how varied and diverse or extensive your simulation data needs to be in order to guarantee this translation.
So there are two things. One is that we learn features that are incorporated with collision avoidance in simulation and also control policy in simulation. So the features that need to represent the objects in the world, they are trained with the static real data that have human annotation. But since the static real image annotation is pretty cheap, we use that. And that doesn't involve actual robot trajectories. So we actually don't learn features representing the real-world objects in simulation. We learn collision avoidance and also policies to reach the target object in simulation, which is the controller.
One more question to Alessandro. For the transfer from RGB to the event-based camera, did you solely use the detection output of the network, or did you also try to use intermediate layers like in the model distillation transfer paper from by Gupta?
No. In general, if you change the sensor modality, it's better if you start off from scratch again. Usually, those kind of works, that kind of works when you do fine-tuning. But here, when you're changing the modality as input, the feature extraction really changes. So you can use a pre-trained early network, but it works as good as starting off from scratch.
Okay, with that, I think we'll conclude the question session. Let's thank all of the speakers. And after this, we'll have a coffee break.